All right, so the example that we're going to focus on today is to find and think about the Galois group of the polynomial f of x equals x to the fourth plus 1 over q. We've talked about this example a little bit before. This is irreducible over q, though seemingly Eisenstein's criterion, and also it turns out the mod p irreducibility test are not helpful in proving that. However, it is actually reducible over the reals. So f of x is irreducible over q, but reducible, just as a comment, over r. You can factor it as the product of two quadratics. We did this, I don't remember if it was Wednesday or Monday, as x squared minus square root of 2x plus 1 times x squared plus square root of 2x plus 1. So you can factor it when you allow real coefficients, plus or minus square root of 2 in this case, that are not rational. But you can't factor it over the rationals. It's irreducible over the rationals. But proving that it's irreducible over the rationals is kind of hard, actually. Anyway, what are we interested in with this? We're interested in seeing if we can compute the Galois group of the splitting field for this polynomial over Q. And then maybe what will that tell us about that splitting field and possible subfields and that kind of thing. So our goal is to calculate, you might say, or determine the Galois group. I'm going to phrase this differently than we've done so far, of f of x over q. So far we've phrased Galois groups as being for a field extension E over the subfield F. Now we're saying calculate the Galois group of a polynomial over Q. That's different. That's a different phrasing, right? What does this mean? It means, i.e., the Galois group of the splitting field for f of x over q. Or technically, you could say a splitting field. There are many splitting fields, though they all would be isomorphic to each other. We will be considering one that is a subfield of the complex numbers. So we need to think about making sure we include the roots, right? We take Q and adjoin the roots of F. That will be the splitting field. What are the roots of F? F of x equaling 0. Since f of x is x to the fourth plus 1 is equivalent to x to the fourth equaling -1. We are after fourth roots of -1 as the roots that we want to adjoin to Q to create the splitting field. What are the fourth roots of -1? Think about what I've taught you about the basics of complex number multiplication. Draw the unit circle in here in the complex plane. This is again labeled with the word real. It stands for the real axis. We pretend this is the real number line here. This axis was labeled with the word imaginary, but it is there. I can see it. All right, it's just a labeling that helps you visualize complex numbers. A general a plus bi, where I is the square root of -1, corresponds to the point with rectangular coordinates AB. And I told you that when you multiply two complex numbers, Geometrically, what happens is you multiply their distances to their origin, their radii, their radial coordinate and polar coordinates, and you add their angles that they make with the positive real axis. Add their angular coordinate when you're talking polar coordinates. And so if you're after a fourth roots of -1, -1's right here. All the fourth roots of -1 also have to be on the unit circle. Because when you raise them to the fourth power, the modulus has to stay the same. The only way that's going to happen is if the point is on the unit circle or at the origin. And the angle, again, has to add. And if I'm raising it to the fourth power, I add it to itself with 4 terms in it. Think about the angles here. This is 180 degrees. So I've got to use a 45-degree angle, 180 divided by 4, to get at, well, 1/4 root of -1 is that point right there. Red. What point is that? Again, this is a 45-degree angle. You can use trigonometry to figure it out. That point has real part equal to cosine of 45 degrees and imaginary part equal to sine of 45 degrees. You can also write this in, by Euler's identity, exponential notation, e to the I times 45 degrees, which technically speaking, you should convert to radians. This is e to the I times pi over 4. But what are the rectangular coordinates of this? Cosine of 45 degrees and sine of 45 degrees are both 1/√2. I should have made my drawing bigger here. I'm going to need to maybe redraw it bigger. 1/√2 plus 1/√2 times I is what this point is. Call this point omega. This is omega. Omega to the fourth power does equal -1. Omega is a fourth root of -1. There are 3 other fourth roots of -1. And they are all, they make a square when you connect the points. They're all 90 degrees apart. 45 plus 90 is 135 degrees. Here's another fourth root of -1. That's 135 degrees right there. If you think about it, that also equals omega cubed. Because omega squared will be, in fact, I. Omega cubed, you add another 45 degrees to the angle and you get to 135 degrees. You're at this point right there. You are at one of these other fourth roots of -1. Add on another 90 degrees to get to 225 degrees. This point right down there is another fourth root of -1. And in fact, it also equals omega to the 5th. And hey, it's also opposite across the origin for omega. It's also the additive inverse of omega. It's negative omega. That might be useful to know. And finally, the last one is over here. That's the last fourth root of -1. The angle, the positive angle this would have with the positive real axis going around this way would be, what would it be, 315 degrees? Is that right? Yeah, 315 degrees. It's omega to the 7th. It's also the opposite of omega cubed. It's also the complex conjugate of omega. I could write all these different symbols for it. Do you feel comfortable with that? Is there anything I can clarify there? These are the fourth roots of -1. Here's an example of how you could confirm that. What is omega cubed, for example, to the fourth power? Well, multiply the exponents. That's the same as omega to the 12th power. Hey, actually, all the powers of omega, including omega squared, omega to the 4th, omega to the 6th, and omega to the 8th, form a cyclic group of order 8, don't they? I only am looking at the odd powers here, but I could include the even powers. They would no longer be fourth roots of -1 if I did. Omega squared is right there. It's I, the imaginary unit. Omega to the 4th is -1. Omega to the 6th is -I, and omega to the 8th is +1. Fourth roots of -1 are also eighth roots of +1. It's a cyclic group of order 8, and therefore I can mod the exponent by 8 here and get omega to the 4th, but omega to the 4th is -1. There would be an algebraic way of confirming that omega cubed is a fourth root of -1. I could do it for the others as well. Omega to the 5th to the 4th is omega to the 20th, mod by 8, the exponent. That's the same as omega to the 4th, which is -1, and omega to the 7th to the 4th is omega to the 28th, mod by 8. That is also omega to the 4th, which is -1. So those are all fourth roots of -1. And yeah, the splitting field for f of x over q would then be, or a splitting field, the most natural splitting field, that would be a subfield of the complex numbers. Q adjoin the roots. Q adjoin omega, comma, omega cubed, comma, omega to the 5th, comma, omega to the 7th is a splitting field for f of x equals x to the 4th plus 1 over q, the rations. It's a splitting field. There are other splitting fields that are, for example, made using factor rings. But this is the splitting field that's a field extension of E and a subfield, of F, which is Q, and a subfield still of the complex numbers. And using the adjoin notation, this is the smallest field extension of Q in C, the complex numbers, that also contains these 4 numbers. But remember, as I've always been saying, it's more than just Q union with these 4 numbers. There's plenty of other numbers in here that have been added to Q, so to speak, infinitely many. Omega, if omega's in there, omega squared's got to be in there. In other words, I has to be in here because omega squared equals I. Omega to the 4th has to be in here. Well, that's -1, you already know, and -1's already a rational number. Omega to the 6th has to be in here. That's -I, that's in there. It's also closed under addition. So for example, adding omega and omega cubed also has to be in there. I wonder what happens when you add omega and omega cubed. What do you get? Let's see, omega is 1/√2 plus 1/√2i. That's omega. What's omega cubed? It's over there. It's, if you think about it, -1/√2 plus 1/√2 times I. Add those together, you get √2 times I. Hey, √2 times I is in E then, which you probably wouldn't necessarily expect ahead of time, right? You know, something involving √2 is in there. You wouldn't necessarily expect that would be the case. Just, I mean, you know, how is all this related to the square root of 2? It doesn't seem like it is. What would happen if you added omega and omega to the 7th? That would also have to be in E. Omega to the 7th is the complex conjugate of omega. It's this thing. And here now the imaginary parts cancel, and this equals √2. √2 itself, the real number, is in E. And there's plenty more examples you could come up with. These things are in E, and this is actually worth knowing if we're going to fully think about this in terms of the Galois group and the tower of fields. What other fields are between Q and E in a lattice diagram? This is actually good information to know. It'll help us to realize these are also in E. And again, the reason they're in E is because E is a field. It's closed under multiplication. It's closed under addition. And there's infinitely more examples you could think about as well. And you could do 7 omega plus 13 omega to the 5th or something. That would be an E as well. Whatever that happened to be. All right, so this is making progress here. However, it sure would be nice to write this as a simple extension of Q. Q of just adjoin one element. And again, when I say that, it doesn't mean just take Q and add one element to it. I mean, with this notation, we only put one element in there. You might hope it's enough to just maybe put omega in there. Is that good enough? Maybe put a question mark here initially. Certainly, Q adjoin omega is a subfield of Q adjoin all these things, right? This is the smallest field extension of Q that contains all of Q and omega. But this contains omega as well. This has got to be a subfield of that. Is this a subfield of that? This is the smallest subfield or smallest field extension of Q in the complex numbers, containing omega, omega cubed, omega to the 5th, and omega to the 7th. But this thing would contain omega cubed, omega to the 5th, and omega to the 7th as well, because it's closed under multiplication and it contains omega. It's a field by definition. That's the smallest one. Therefore, this one's got to be a subfield of that too. They are equal. The answer is yes. They are equal. That's always nice when you can write your field extension as a simple field extension, because then it just makes it easier to think about. Let's continue thinking about it now. What else do we know then about this? Omega is a root of f, and f of x is irreducible over q. And it's 4th degree. We know that means q of omega is a degree 4 field extension of q. As a vector space over q, it's 4-dimensional. It's got a basis with 4 elements. Let's write that out. F of x equals x to the 4th plus 1 is irreducible over q. We already mentioned that. Therefore, the degree of q adjoin omega over q is 4. And we can also say we can write the elements of q omega as linear combinations of omega to the 0 power, which is 1, omega to the 1st power, omega squared, and omega cubed. Before this point today, I've been using like C's with subscripts. Let me go ahead and just do what I do in the lectures now. I'll write A, B, C, D, and D for the coefficients. A times 1 plus B times omega plus C times omega squared plus D times omega cubed, where A, B, C, and D are all rational numbers. There's your general form for an element in this field extension of Q. In other words, i.e., 1 omega omega squared omega cubed is a basis for Q adjoin omega as a vector space over Q. You should know all these things. We've been talking about them a fair amount here. This is true even though omega and omega, excuse me, even though 1 and omega squared are not 4th roots of -1, right? We started this problem by thinking we wanted to think about 4th roots of -1, the zeros of f of x. What's the splitting field for this thing? It is Q omega, and Q omega does contain, for example, 1 and omega squared, even though those are not 4th roots of -1. All right, now what about this Galois group thing? And how will that, again, what's the goal with the Galois group and the fundamental theorem of Galois theory? For us, at least, the goal is to understand the tower of fields containing both this field extension and Q and any subfields of E in between. That's our goal. It's a manageable goal for us. Galois was motivated to show that a certain quintic was not solvable by radicals, which is a much loftier goal. But this is still worthwhile and interesting that you can do this. So what is the Galois? The Galois group of this polynomial over Q is the same as the Galois group of the field extension, which is the splitting field over Q. So that can be written this way, Q of omega over Q. I mentioned this the other day, I'll mention it again. By problem number 1 in chapter 32, any automorphism of a field extension of Q will automatically fix everything in Q. Therefore, when your base field is Q, this is the same as the group of all automorphisms of the field extension. That's not the case when the base field is not Q in general. But if the base field is Q, again, problem number 1 in chapter 32, which we talked about briefly on Wednesday, says that any automorphism of the field extension of Q will automatically fix everything in Q, since the base field is Q. See exercise 1. So what is this? I need to think about automorphisms of this that fix Q. If alpha is in this Galois group, if it is an element of it, it might be helpful to think about a possible formula for alpha. And one way to think about a formula for alpha is to use the vector space description of this Q omega. What is alpha of a general element of Q omega, meaning what is alpha of A plus B omega plus C omega squared plus D omega cubed? I'll put a question. What is it? We don't know. It does have to fix Q, so one thing I can say right away is if B, C, and D are all 0, it's got to map A to A. That's worth noting. If B, C, and D are all 0, then alpha of that thing is alpha of A must be A, because elements of this Galois group fix the rationals. The other important thing to note, this is perhaps the most important observation for the entire day today here, is to think about what alpha would do to omega, and what would that imply about what it does to powers of omega. Now, omega is a fourth root of -1. In other words, it's a root of f. Omega to the fourth plus 1 equals 0. Therefore, alpha of omega to the fourth plus 1 must equal alpha of 0. Just plugging in both sides into alpha, my arbitrary element of this Galois group. Alpha is a function, right? An automorphism q omega, so it's an isomorphism from q omega to itself. It's 1-to-1 and onto in doubly operation preserving. We know from way back in chapter 6 about isomorphisms and even homomorphisms in chapter 10 that they map the 0 element to the 0 element. E to E back in chapter 6. And we also know since this is a ring homomorphism, field homomorphism actually in this case, it's doubly operation preserving. This would equal alpha of omega to the fourth plus alpha of 1. And that's going to equal alpha of omega to the fourth, right? Because omega to the fourth is omega times omega times omega times omega. Alpha preserves multiplication. That would be alpha of omega times alpha of omega times alpha of omega times alpha of omega. And since alpha is an automorphism, it's an isomorphism, it also maps 1 to itself. It also fixes rationals. Alpha of 1's got to be 1 as well. In other words, what do I have here? I have that if omega is a fourth root of 1, so it satisfies this equation, then alpha of omega also satisfies the same polynomial. It's another root. Therefore, alpha of omega is either equal to omega or omega cubed or omega to the fifth or omega to the seventh. There's 4 possibilities. For what alpha can map omega to. Hey, and omega cubed and omega to the fifth and omega to the seventh themselves are fourth roots of 1. By the same argument, alpha of omega cubed must either be omega or omega cubed or omega to the fifth or omega to the seventh. Alpha of omega to the fifth must be either omega or omega cubed or omega to the fifth or omega to the seventh. And alpha of omega to the seventh must be one of the 4 possibilities as well. But do I have complete freedom in deciding what they would be? No. If, let's consider it case by case, if alpha of omega equals omega, then alpha of omega cubed, since alpha is doubly operation preserving, would be alpha of omega quantity cubed, which would be omega cubed. In other words, alpha would map omega cubed to itself. It's also going to map omega to the fifth to itself. And it's also going to map omega to the seventh to itself. You do not have complete freedom in deciding what the other things get mapped to. In fact, when you know what omega gets mapped to, the other ones are completely determined. If alpha maps omega to itself, it's going to map the other things to itself. And ultimately, alpha would be the identity mapping epsilon. This entire thing would get mapped to itself if omega gets mapped to itself. If alpha of omega equals omega cubed, the other things are still completely determined. alpha of omega cubed would then be alpha of omega quantity cubed, which would be omega cubed cubed, omega to the 9th. Remember, the powers of omega form a cyclic group of order 8 here, so this is the same as omega. What about alpha of omega to the 5th? That'll be alpha of omega quantity to the 5th. That'll be alpha cubed to the 5th, which is, excuse me, omega cubed to the 5th, plus, which will be omega to the 15th. Mod the exponent by 8 is the same as omega to the 7th. Alpha of omega to the 7th will be alpha of omega quantity to the 7th, which will be omega cubed to the 7th, which will be omega to the 21st, mod the exponent by 8. This is the same as omega to the 5th. So if alpha maps omega to omega cubed, it maps omega cubed back to omega. It maps omega to the 5th to omega to the 7th, and it maps omega to the 7th back to omega to the 5th. These things are permuting the roots. I could even write this stuff in permutation notation. I could write with this example, I could write alpha as a product of 2 cycles, where the elements of the 2 cycles are not 1, 2, 3, 4, 5, etc., like we talked about back in chapter 5, but these different roots. Omega gets mapped to omega cubed, and omega cubed gets mapped back to omega. Omega to the 5th gets mapped to omega to the 7th, and omega to the 7th gets back to omega to the 5th. This is a product of 2 cycles. Permutations, chapter 5. Just using different symbols for what's getting permuted. These things are very much related to permutation groups. That's historically how group theory got started when Galois was studying this stuff. He was thinking about how these roots get permuted. He was essentially studying permutation groups without calling them permutation groups. So the special examples came before the abstract theory. Galois lived in the 1820s or something, 1830s. The group theory as an abstract theory didn't get developed until like the 1870s or 1880s. So Galois was like 50 years ahead of his time. But that's kind of how math develops, from special examples to more general theory. You know, in books, you get the general theory with examples to help you. But in real life, math develops by thinking about special examples, special cases, and then seeing connections between the special cases to construct the theory, the axiomatic theory. There's 2 more possibilities here again. If alpha of omega equals omega to the 5th, then what's alpha of omega cubed? It'll be alpha of omega quantity cubed. That'll be omega to the 5th cubed, which will be omega to the 15th, which will be omega to the 7th. If omega gets mapped to omega to the 5th, then omega cubed will get mapped to omega to the 7th. What does omega to the 5th get mapped to? Omega to the 25th, mod the exponent by 8, you get omega. Alpha, in this case, is permuting omega and omega to the 5th back and forth. It's evidently going to permute omega cubed and omega to the 7th back and forth. Get omega to the 35th, mod the exponent by 8. That's the same as omega cubed. Isn't this kind of fun? You may still feel like you don't fully understand it. And I certainly don't understand everything about Galois theory, but this stuff is kind of fun. The last possibility is if alpha of omega is omega to the 7th, then what can you say about the other elements? Omega cubed will get mapped to omega to the 21st, which when you mod the exponent by 8 is going to be omega to the 5th. Omega to the 5th probably gets mapped back to omega cubed. It seems like these things are products of 2 cycles. So this is omega to the 7th to the 5th, which is omega to the 35th. Mod the exponent by 8, you do get omega cubed. And I bet alpha of omega to the 7th will be omega. Omega to the 49th mod the exponent by 8 does give you omega. It also could be handy to figure out, say, what I gets mapped to. Say in each of these 4 cases, these are all 4 different examples, right? 4 different possibilities for alpha. Say we're in this case right here, what would I get mapped to? Well, I is omega squared. This is going to get mapped to alpha of omega quantity squared. And if omega gets mapped to omega to the 7th, this is omega to the 7th squared, which is omega to the 14th. Mod the exponent by 8, you get omega to the 6th, which is actually negative I. So if omega gets mapped to omega to the 7th, then I gets mapped to negative I. And I could keep going. I could do lots of other calculations. Can we figure out what the square root of 2 gets mapped to? Which might be a good thing to know because square root of 2 is in E. In, say, this case here, maybe to help us, we want to figure out what 2 gets mapped to. Well, 2 gets mapped to itself because it's rational. 2 is also the same as square root of 2 squared. Well, alpha's doubly operation preserving. This will be alpha of square root of 2 squared. So in other words, alpha of square root of 2 squared equals 2. Alpha of square root of 2 has got to be plus or minus square root of 2 because its square equals 2. Can I decide which one? Would it be plus square root of 2 or minus square root of 2? I think it's plus square root of 2, though I'd have to do maybe more calculations to see. Because I think this particular mapping is essentially complex conjugation. If you look at the picture, omega is getting mapped to omega to the 7th. It's getting reflected across the real axis. Omega to the 7th gets mapped back to omega. Omega cubed and omega to the 5th get swapped. They're reflections across the real axis from each other. I gets mapped to negative I. Those are reflections across the real axis. I think things on the real axis are going to stay fixed, even if they're irrational, like square root of 2. I think with this example, it's going to be plus square root of 2, but I haven't fully proved that. Continuing thinking about this particular example, so we're in the case where alpha of omega equals omega to the 7th. Alpha of omega cubed equals, in this example, omega to the 5th. alpha of omega to the fifth equals omega cubed, and alpha of omega to the seventh equals omega. This particular example, again, does also have the property that alpha of omega squared equals alpha of I equals negative I. We saw that. And it would also have the property of alpha of omega to the sixth would equal alpha of negative I, would turn out to be positive I. And we don't need all this information to write the general formula for alpha in this case. I wanted to write it down anyway. Alpha of a general linear combination of an element of Q adjoin omega. What would this formula be? Well, it's got to be operation preserving. So I would be able to write this. Oops, forgot my omega cubed here. A, B, C, and D are all rational numbers. So alpha of A is A, alpha of B is B, alpha of omega is omega to the seventh. Alpha of C is C, alpha of omega squared is negative I. Which is the same as omega to the sixth. And alpha of D is D, and alpha of omega cubed is omega to the fifth. I could write this, but what would be most ideal is to write all these things in terms of the basis, 1 omega, omega squared, and omega cubed. Omega to the seventh is the opposite of omega cubed. Negative I is the same as omega to the sixth, which is the opposite of omega squared. And omega to the fifth is the opposite of omega itself. In other words, this can simplify to A minus B omega cubed minus C omega squared minus D omega, which could also be written A minus D omega minus C omega squared minus B omega cubed if you write it in the order of the basis elements being 1 omega, omega squared, and omega cubed. Comes back to this picture. Raise omega to the sixth power, you have to add 45 degrees to itself. You have to multiply it by 6. 6 times 45 would be that angle. It would be 2 omega to the fifth. I think there's no mistakes here. This would be the formula for alpha in this example. This equals this. Now, I haven't proved this is doubly operation preserving. In fact, to derive this formula, I'm assuming it's doubly operation preserving. Probably is a worthy exercise to show it's doubly operation preserving in some way when you have that this is defined to equal that. In the Mathematica exercises, I do have Mathematica check it sometimes. In the solutions. Again, I derived the formula assuming these things are true and assuming it's doubly operation preserving. But if I just had that this is defined to be this, you could also ask, is that really double? Is it going to be doubly operation preserving? The addition operation preserving turns out to typically be easy. It's the multiplication that's hard. It's really messy. Where were we going with all this again? We were trying to figure out the Galois group to ultimately help us figure out about the tower of fields. We're almost there now. These are just calculations you should be able to do. Though I don't remember. This kind of detail doesn't come up on the final exam, but as you've already seen. But it's still good to learn about to try to understand it. Since there's 4 possibilities for what omega gets mapped to, either omega, omega cubed, omega to the 5th, or omega to the 7th, that means the Galois group has 4 elements, 4 functions in it. The book makes a little table like this. They put the Galois group elements on the top of the table, and they put what they map things to underneath. And it's good enough in this case to just say what omega gets mapped to. Epsilon is going to map omega to itself. Epsilon is going to be the identity element. I've been calling this function alpha all along. I'll call another function alpha, but this time alpha is going to be something specific. It's going to be the one that maps omega to omega cubed. Use another Greek letter for another one, call it beta, say beta maps omega to the 5th. The last possibility has got to map omega to the 7th. What should I call it? Well, I believe it will equal alpha compose beta, though we might want to check that. It should, it turns out. Alpha compose beta of omega is alpha of beta of omega. Beta of omega is omega to the 5th. If I assume alpha's operation preserving, I can say this, which gives me this. Mod the exponent by 8, that gives me omega to the 7th. Yes. If alpha is this mapping and beta is this mapping, this one's got to be alpha compose beta. It also actually, in this case, has to be the same as beta compose alpha, because this is a group of order 4, so there's only 2 possible things it's isomorphic to. It's either cyclic of order 4, Z4, or it's isomorphic to the external direct product of Z2 with itself. Got an inkling about which possibility it is? Yeah. These 3 things all have order 2, not order 4. You can verify that. The Galois group here is not cyclic. It's isomorphic to the external direct product of Z2 with itself. Therefore, by the fundamental theorem of Galois theory, we can take the lattice of subgroups of this thing and make a correspondence with the tower of fields, call it a lattice of fields, for the field extension. The lattice of subgroups, subgroup lattice of the Galois group is going to look like this. There's the entire Galois group, which consists of 4 elements, epsilon, alpha, beta, and alpha beta. Then there are going to be 3 subgroups of order 2. That's different than a cyclic group of order 4, right? A cyclic group of order 4 only has 1 subgroup of order 2, only has 1 element of order 2. Here in the non-cyclic subgroup of order 4, we've got 3 distinct subgroups of order 2 generated by the elements of order 2, alpha, beta, and alpha compose beta. So the fact that it's not cyclic is going to imply something about the corresponding tower of fields. And then you've got the trivial subgroup generated by the identity. That's our subgroup lattice for the Galois group. The corresponding tower of fields is same kind of structure. Technically speaking about it, you should think about it inverted, but we draw it with the bigger field on the top typically. And there's more you can say. These subgroups of the entire Galois group all have index 2, right? The number of left cosets of in each case is going to be 2 because of Lagrange's theorem, chapter 7. The order of the entire group is 4. The order of each subgroup here is 2. 4 divided by 2 is 2. The index is 2. It's also 2 for each of these. And that in the tower of fields is going to imply corresponding degrees of vector spaces of the bigger fields over the smaller fields. What will the tower of fields look like? It's actually a bit tricky to write it down here in this case, trickier than you would hope. It will have a similar structure. I put Q of omega on top and Q on the bottom. I am going to have 3 intermediate fields in the tower of fields that correspond to 3 intermediate subgroups in the lattice, subgroup lattice of the Galois group. And these degrees that you label these lines with are still going to be all 2s. So whatever this is, it's going to be a 2-dimensional vector space over Q. This is going to be a 2-dimensional vector space over Q. This one's going to be a 2-dimensional vector space over Q. And then also Q of omega is going to be 2-dimensional over each of these subfields. As vector space over those subfields. But what are those subfields? Well, they'd be the fixed fields of the different possibilities, which gets a bit tricky to figure out. Back to this example, I'm wondering if I made a mistake here, because it seems like this is maybe not right. You'd have to ask what elements are going to get mapped to themselves. Certainly everything in Q does, but it should be a bigger fixed field here for this. I'm talking about really is the fixed field for epsilon and this particular automorphism. I'd have to ask what conditions on A, B, C, and D will make these 2 things equal. And it seems like the key conditions are that A can be anything. C would have to be 0 to make these equal. And B would have to equal -D, seems to be the condition. So you'd be talking about elements of the form A plus B omega plus C omega squared minus B omega cubed. If I want these to equal, again, D would have to equal -B. So the fixed field is going to, actually, and C has to be 0. This has to be 0. So the fixed field is going to consist of all elements of this form. Which means I'd want to figure out what is omega minus omega cubed. Omega minus omega cubed is 1/√2 plus 1/√2 times I minus omega cubed was -1/√2 plus 1/√2 I. I'm subtracting those. Looks like this gives me √2. Elements that get fixed under that particular automorphism are elements of this form, which are elements of this form, where A and B are rational, which would be Q adjoin √2. Q adjoin √2 would be one of these fields. Q adjoin root 2 would be one of them. I do want to end class early. I'm not saying what these other ones are. This is an exercise that I wrote a solution for, so you can look it up. A long exercise. That's one of them. That would be the fixed field for this particular example that maps this to this. But there's other examples based on these different ones. Then this getting mapped to this, I guess it was based on this one. It would be, this would be alpha beta is what this would correspond to. This would be the fixed field. This would be the E sub epsilon comma alpha beta, according to how I chose to name these things here in this table. And the fact that this example was constructed by assuming omega got mapped to omega to the 7th. That's how I made this example. It's got to be that one. Using the fixed field notation, E sub h in general. This is going to be the subfield of Q omega and a field extension of Q where everything in here gets mapped to themselves under these two automorphisms. Doing all this without looking at the statement of the fundamental theorem of Galois theory, because the statement is really complicated. In essence, I'm illustrating the theorem. Certainly, we're not proving it. Very long and complicated theorem. You know, you can see on your final exam, you're not going to have to state this or anything. Essentially, we are illustrating certainly properties 1 and 3 when I've been talking about this stuff. We've been talking about the indices and the degrees. That's property 1. Property 3 is relating fields in the tower of fields to fixed fields. You've seen in the take-home final what's there. The main thing, one of the problems tries to emphasize is, I say, suppose the Galois group is cyclic of order 6. It's isomorphic to Z6. To get to the conclusions you want in that problem, you need to think about what the subgroup lattice looks like. And cyclic groups have actually very simple subgroup lattices because of the fundamental theorem of cyclic groups back in chapter 4. Right? You didn't say what they are. They have a unique subgroup of each possible order. That's a divisor of the order of the entire group. Cyclic groups have unique subgroups of each order. So the lattice is just a line, essentially, not one of these kinds of things. Lecture 37, I did an example. I talked some about the example in the book where the Galois group turns out to be isomorphic to S3, the symmetric group on 3 objects. That's a more complicated example. That's the one where I made the mistake that I sent you about. If you really want to round out your understanding more here before you work on the exam, I would suggest studying example 4 and 5. 4 is related to what we did in class on Wednesday. 5 is the example I did in the lecture 37 with the mistake. The subgroup lattice is a subgroup lattice related to S3. S3, right? It's got 6 elements, 3 factorial. It's also isomorphic to D3, the dihedral group of order 6 symmetries of an equilateral triangle, because D3 and S3 are isomorphic. It stops there. D4 is not isomorphic to S4. D5 is not isomorphic to S5, but D3 is isomorphic to S3. So if you want to round out your understanding more, I'd suggest really studying examples 4 and 5 especially. Wow, what a subject, huh? The class, Eric Gossett always says this is the toughest class at Bethel. I don't know. I personally think quantum mechanics might be tougher, but certainly it's plenty tough here. Real analysis in some ways is tougher. In some ways it's easier. Real analysis seems easier in some ways because it's like a more familiar kind of subject related to calculus. But it also seems harder sometimes because the proofs generally are harder. The proofs are much more subtle in real analysis, trickier. Algebraic proofs, sometimes you can figure out what they should be by guessing, right? What's the natural thing to do? Once you got enough experience, you realize, oh, this is the only thing I can do. So in that sense, they're easier, but certainly the subject is very abstract and you'll learn things you would never imagine are true. So I hope you enjoyed that part of it to some degree. And yeah, we'll see you next week. You can certainly turn your exam on paper in person. You can also email pictures. Okay. Have a good weekend. Mm-hmm.